Okay, in this video we're going to jump into two-dimensional motion. And the first thing we're going to take a look at is a horizontal projectile. And this is going to require you to kind of simultaneously do two things, realize two things are happening at once, and both of them are independent of each other. Let me explain that further. Okay? So if we were to have, say, a small object, let's just say like a golf ball, and it were to be rolling along a flat surface, and then all of a sudden it reaches the edge of that surface, like a cliff or an edge of a building or something, and it's moving horizontally at 12 meters per second. Well, once it leaves the edge of this building, it's going to start falling down, and you notice it's going to take a pathway like this, but it doesn't look like a nice parabola like we've worked with before. So we need to take a look at how this is actually going to, how we're going to end up calculating what's going on both horizontally and vertically. Okay. Now, the first thing to recognize is we have an initial velocity that's going to make it go horizontal. But in terms of vertical forces, we're not pushing this ball down. We're not throwing it up. It's going to just start from rest. Once it gets to the edge of this building or whatever that is, it's going to just start from rest like we dropped it, and it's going to drop at a certain rate, just like our free fall situations. Okay, so it's going to start dropping based on gravity as soon as it leaves this building, and that operates completely independent of how fast it was going this way. Okay, this velocity has no effect on what happens this way, and that's a kind of a tough hill to climb, so to speak. It's one of those things that doesn't sit well at first. We're going to work on that a lot in class on why things operate independently when you have forces operating in different directions. So let's take a look at the mechanics of how we would approach this. Okay, we need to look at this in two different lights: what's happening vertically and what's happening horizontally, because they're both happening as though the other one didn't exist. One does not affect the other. So what I'm going to do to analyze this is I'm going to write horizontal, and then over here I'm going to write vertical. I'm going to do two separate calculations. Now horizontal and vertical are definitely related to each other, but it doesn't mean one actually affects the other. I'm going to start with the vertical just because I don't know, that's one that we're more used to doing after our free fall stuff. So what I want to do is I want to analyze this as though it wasn't even moving that direction. If it just was dropped, how would things behave? Okay, so let's list the things that we could possibly know. We know initial velocity, final velocity, acceleration, time. What else could we? How about the height, or how far it goes? There's some different things that we may or may not know. So let's take a look at this situation and label what we can figure out. Okay, the height that's going to drop is eventually it's going to go 40 meters before it hits the ground. Okay. Do we know how long it takes to get there? No, not yet. Initial velocity. If it's being dropped from rest, it's not being thrown down, it's not being thrown upward, then basically we have 0 for our initial velocity, 0 meters per second. Do we know how fast it's going to be going at the bottom? No, we don't know that either. How about acceleration? Okay, gravity is what's pulling this thing towards the earth, and we know that the acceleration is 9.8 meters per second squared, but what we really need to ask ourselves is it slowing down or speeding up? And if we drop this from rest, it's going to be speeding up. It's going to make this positive 9.8 meters per second squared. So really we know 3 out of these 5 things. Let's take a look at our acceleration equations, okay, and keep in mind that's what these are. This is when something is accelerating at a constant rate. So it's constantly speeding up or it's constantly slowing down. Okay, let's pick one of those and just see what we can figure out. Okay. So how about, let's take a look at one of these maybe easier equations to work with. Let's not jump into the toughest one that we have. If we were to look at this, there's a problem. That's a nice easy equation to work with, but we don't know the time, and we don't know the final velocity. We got 2 variables there. We can't solve for one if we got 2 things we don't know. So let's work our way down. What else can we figure out? Could we work with this one down here? Well, we don't know the final velocity. We do know the acceleration. We do know the distance, the x value. In this case, you can call it y. Okay, we know the initial velocity, so we could use that one to our advantage. Could we also use this one up here? Let's see, we know the distance, it ends up going 40 meters. Started at 0. Initial velocity, is going to be 0, so that goes away. We don't know the time, but we could solve for that. So both of these, it looks like both of these we could actually use to our advantage. We pick one or the other. Okay? So I'm going to take a look at this one right here. I'm going to say, all right, x final equals x initial plus velocity times time plus 1/2 at squared. Okay? So I've got that equation. Now let's look at what we can plug in. We know the final position that it's going to be at is going to be 40 meters. The initial was 0. The initial velocity is 0, so that means this is going to go away. That's going to go away. Those are both zeros. I don't even need to put the zeros in. 1/2 9.8 t squared. Okay. That's not going to be too hard to solve. I can take this value right here, which ends up being 4.9, half of 9.8, divide it over here, take the square root, and when I solve that, I'm going to get a time in this case of 2.86 seconds. Okay? So at 2.86 seconds right there. So it's going to take, this is going to hit the ground at 2.86 seconds. All right? Now, that's time. I figured that one out. Could I figure out the final velocity also? Sure. I could plug that in right here. If I need to find the final velocity, I'm going to do initial velocity, which is 0, plus 9.8 times 2.86. That's how long it's in the air. And the final velocity, in this case, is going to come out to be 28 meters per second. Okay. Now, I want you to think briefly about what that means. I'm dealing with the vertical situation. So it means it's going to hit at 2.86 seconds and it's traveling downward at 28 meters per second right when it hits the ground. But that's only the downward component. It's how fast it's moving towards the earth. It doesn't have anything to do with how fast it's moving horizontally. So I basically figured everything I can out about that vertical situation. Now it's time to take a look at what's happening horizontally. And there is one big connecting factor here. No matter which one we're looking at, both of them deal with the same time. Okay, this is our connecting rod. Okay, the time of flight. So it's going to be in the air for 2.86 seconds. Whether we're looking at the horizontal movement or the vertical movement, that time of flight is the same value no matter how we look at it. So I know the time is going to be 2.86 seconds. Okay. Now, there's a fundamental difference here. Vertically, we let this thing go off the edge of the building, it's going to start speeding up as it goes down. But horizontally, there's nothing to get in its way. Okay? It's not going to speed up and it's not going to slow down. In reality, there will be some air resistance, but we're going to neglect air resistance here. And if we don't include that friction from the air, there isn't anything that's going to slow this down. It's just going to keep going at 12 meters per second. Air is the only thing that could possibly change that. So if we're going to ignore air resistance, it's not speeding up and it's not slowing down. It's just traveling 12 meters per second until it eventually hits the ground. Okay? It's speeding up in the vertical direction, but staying constant in the horizontal. If it's staying constant, then we do not, we use none of those. We do not use any of those equations. None of those apply. Those are all applied for constant acceleration situations, where it's speeding up at a rate or slowing down at a rate. It's not happening, so we're not going to use any of those. We're going to go back to our basic definition of velocity. Constant velocity, that is distance divided by time. That's the change in distance divided by the change in time. Okay? So I've got time down here. Do I have its velocity? Well, I sure do. It's not changing. It's 12 meters per second. What's the only thing I don't know here? I don't know the distance. I don't know how far it's going to travel horizontally. But all I need is these two things and one simple equation. Okay, now I got to rearrange that equation to fit what I'm trying to do. If I want to solve this for distance, I'm going to multiply time over to this side. So distance is going to be velocity times time. So I'm going to plug in a velocity of 12 meters per second and a time of 2.86 seconds. My seconds cancel out. And I'm going to be left with the distance that this would travel. Okay. And this ends up traveling 34.32 meters. Did I get that right? Yep. And I basically figured out everything there is to figure out about this. Now, the fundamental things to watch out for. The vertical is always accelerating because gravity will do that. The horizontal is going to remain constant as long as we're ignoring air resistance. And that's a hard thing for us to account for at this stage of the game. We're going to ignore that air resistance is there and assume it's something, minimal, is not really going to affect that much. Okay, the big deal is vertically you use your your acceleration equations. Horizontally you use your constant equations. Okay, and the only thing that they will share in common is the time. Everything else is different vertically than it is horizontally, and those two things operate independent of each other. If I kick this off that hill at 15 meters per second, it wouldn't matter for this. It doesn't affect how long it takes it to hit the ground. Okay, that's what gravity does. This speed doesn't affect this speed. But the two of them share the same time of flight, and we can use that to connect the dots.